right, welcome back, gang. This week we're going to continue our Physics 8 live stream with a new chapter called Oscillations, or specifically simple harmonic motion, which is a specific type of oscillation, as we'll see. And this is a chapter that's kind of in the middle between all the stuff we did in mechanics before, such as maybe kinematics or conservation of energy, and waves. And we're going to study a very specific type of motion called oscillation, and well, we are going to use some of the stuff we've learned before, but we are going to have to introduce some new things because this is a very different type of motion. Because the only way you can oscillate back and forth, it turns out, is if your acceleration is changing all the time. In other words, we are no longer going to have constant acceleration. Now, I know I said at the beginning of the semester that in Physics 8a, acceleration is going to always be constant. That's why we have the kinematic equations that we have and so forth. And that was true, kind of. It was true up until now. But it was easier to say that and to be, very broad, because that's still true for all of the mechanics we've done before. It's just that now, if we're going to study oscillations, we are going to have to grapple with an acceleration that's not going to be constant. It's going to be a function of time, and the acceleration itself is actually going to oscillate too. So it is what it is. It means that we're going to talk about kinematics somewhat, but usually conservation of energy is going to be our go-to, and we'll see that in problems. But what we have to do is describe what we mean by oscillations, what kind of oscillations we're going to study, and we have to give a mathematical model or at least an equation that is going to represent that type of oscillation. And that's kind of the tricky part about oscillations. There's a whole part that is just math that we need to talk about, at least a minimum, so that you then see how that baseline of math actually permeates every oscillator you're going to see. Now, for the most part, you're going to see two. You'll see the mass and spring oscillator, usually horizontal, but sometimes vertical, and then the simple pendulum. But there's also a couple of other oscillators that you might come across. So, you might see those maybe in discussion or on specific problems. The point being that there's a foundation in math that kind of needs to at least be presented. Nobody expects you to be experts at that type of math, but it'll help tie everything together when you look at the whole chapter. So let's start with a definition. Oscillatory motion is a repetitive, periodic motion back and forth about an equilibrium position. Okay, this is really important. There has to be an equilibrium position about which oscillations take place. And with that said, what we need to do is we need to be a bit more specific about what we mean by oscillations. So let me try to do this as generally, but also as simply as possible. Let's say that a quantity, x as a function of t, will undergo oscillations. Now, specifically, simple harmonic motion, which is a very specific type of oscillation, if it satisfies an equation of the form d2x dt squared plus omega squared x is equal to 0. Now, x could be anything. Typically, it would be maybe the position of your oscillator. Could be theta, the angular position of your oscillator if you have a swing, right, a simple pendulum maybe. And the idea is that if I can establish an equation that looks like this, that involves x, whatever x may represent, then that quantity x is going to oscillate. Okay, and it's a specific type of oscillation. Okay, it's called simple harmonic motion. It is oscillations that go on forever. There's no damping, there's no energy loss. It's just back and forth motion that goes on forever, which I grant you is idealized. That's true. And if you were to, sit a child on a swing, pull the swing back and let the swing go, eventually, of course, the child would stop swinging if you didn't keep pushing him or her every time he swung back up, right? So in real life, oscillations do end, but what we get to say is that, well, you know what? If we only study 2 or 3 swings back and forth of the child, there's not that much difference between all 2 or 3 of them. You can basically ignore any energy loss and it's reasonable. Okay, now why do we do that? Again, we could make our life really hard and include damping off the bat, but how about if we have a nice simple model so that we can learn to walk before we run, and we can describe oscillatory motion reasonably, perhaps not perfectly, but reasonably in some cases. Okay, so this quantity, if I can put it in this form, it will be a quantity that oscillates, that goes back and forth. Okay, and we'll say that it x of t will then oscillate following well, let's say this. Let me say that a little bit differently. We'll then oscillate with angular frequency omega, which we'll redefine that in a second, but angular frequency omega according to, now what does x of t look like? Well, if I have an equation like this, which is called a differential equation, it's a second order differential equation with constant coefficients, doesn't matter. Nobody expects you to know how to solve it. Everybody expects you to understand that the solution, though, looks like this. Okay, x of t is going to be equal to capital A, which is going to be the amplitude, cosine of omega t plus phi sub c, or you could write the same thing with sine instead of cosine. A sine omega t plus phi sub s. Now, just as a matter of notation, and this is my notation, I call phi sub c the constant associated with cosine, phi sub s the constant associated with sine. That's just to designate that they're different. A lot of books just call the constant phi. It's the phase constant. This is called the phase, the whole thing. Phi sub c or phi sub s is called the phase constant. We're going to talk about that in a second. And a lot of textbooks just call it phi, which I find misleading because then you think that, whether it's cosine or sine, it's going to be the same thing, and it's not. Phi sub c will never be the same as phi sub s. Now, how do you deal with this or thing here? Well, you can pick either one. You can pick x of t like this. You can pick x of t like this. You might even find, depending on who's teaching and how they prefer to present this, you might even find something like this, c1 cosine omega t plus c2 sine of omega t. It's the same thing. You can actually use trig identities to go from this to this and vice versa. So the point is, it's a cosine or a sine or a combination of the two. I prefer this because you pick one of the two, unless the problem tells you which one to pick, and you just run with it. And it doesn't matter if you choose sine or cosine. Phi will change accordingly and will, make your function work. So oscillations are back and forth motion about an equilibrium position. Specifically, we study oscillations where the quantity that oscillates, let's say x is the position along the x-axis of my oscillator, satisfies this, and if so, this is what x looks like as a function of time. Okay, so let's do two things. Let's graph one of these. Doesn't matter which one, they're going to both look the same. And then let's define all these quantities, because we need to know what A is. We need to know what omega is and what it represents and what it does, and same thing for phi sub c or phi sub s. Okay, so this thing is going to look like a sine or a cosine. So let me just graph something that's somewhat realistic here. All right, so it's going to look something like this. Maybe let's add one more just for good measure. Okay. So this is going to represent oscillations that never stop. Okay. This height here doesn't decrease as time goes by. This thing just goes on forever. Okay. And we're going to have two dotted lines here that are going to bound this graph. This is going to be x equals a. This is going to be x equals minus a, because cosine and sine oscillate between minus 1 and 1. So a cosine and a sine oscillate between minus a and a. And then we can define these different quantities. So first of all, a is the amplitude. It's a distance, so it should be in meters. Sometimes you'll find it in centimeters because it's a bit more practical. Okay, and this is the furthest distance from equilibrium reached by the oscillator. So the furthest distance from equilibrium reached by the oscillator. Okay. Which means, of course, that, okay, yeah, this is A, and this would be your equilibrium, x equals 0. In this case, you'd be oscillating back and forth about x equals 0. Okay. So that's amplitude. Omega is angular frequency. That's going to be in radians per second. And omega is going to be 2 pi times f, which is the frequency, or 2 pi times capital T, which is the period. Okay, which isn't helpful because we don't know what either of these things are, but we're going to define them in a second. The angular frequency omega does not represent anything that makes physical sense. It is a quantity constructed based on what the period is, and it is such that its goal is to make sure that this function or this function resets every time t reaches a period. So let's explain what a period is so that at least that makes sense. The period is the duration of of one full oscillation, basically. Right? If you take one pattern, the fundamental pattern of this oscillation is what I highlighted, the amount of time it takes for that full oscillation to occur is going to be t. Right? If we start at 0, this is t. Now, of course, it's also true that the time from here to here is t, the time from here to here is t, and so on and so forth. But t is the period of oscillation. So t is the period of oscillation. It is going to be in seconds. It is the time to complete one full oscillation. And then f is the frequency. Now frequency is going to be in 1 over seconds, which is hertz. This is the number of oscillations
completed per second. Now that's probably not going to be a very high number if what you're studying is a child swinging on a swing, right? How many oscillations can you complete in 1 second? Hopefully very little, less than one actually, hopefully, for the sake of the child. But the point is that's what it measures, right? Now, not everything is a swing going back and forth, so frequency could be a number of computations per second. If you're thinking about a computer, you can get frequencies that go very high, megahertz, gigahertz, and so on and so forth. So you can have a whole bunch of oscillations occur in 1 second depending on what is oscillating. But when it comes to mechanical oscillators, it's typically not going to be a whole lot, right? Because the period is probably going to be on the order of seconds, maybe a tenth of a second, depending on what you put together. But usually this type of motion takes more than 1 second to complete one full oscillation. Anyway, that is period and frequency, and that's how they tie into angular frequency. Of course, period and frequency are related to each other, where we have t is going to be 1 over f, or if you prefer, which might make more sense, f is going to be 1, which represents 1 second, divided by t, which is the time it takes to complete one oscillation. Okay, and t, of course, if you think of it, let's do, there we go. The bigger you make t, the smaller you make omega. Now, the bigger you make t, the further out this goes, and so the longer it takes to complete one oscillation. So omega, if omega is small, then that stretches the wave, or the sine of the cosine, not the wave, the sine of the cosine out. Right? If omega is very small, that's because I lost track of what I was saying. Let me say this again. if t is very large, then omega is very small. So if omega is very small, it's going to take a long time to complete one full oscillation. But if t is very small, if the one oscillation happens very quickly, then omega goes up, and if omega goes up, then the cosine or the sine gets more packed together. You get more oscillations in 1 second by definition. Okay, so that's what that represents. Now, what does phi represent? Or phi sub c or phi sub s? Okay, so phi sub c and phi sub s. Effectively, they're the same quantity. Again, the subscripts are just to denote that they're not the same value if you use cosine or sine. These are angles in radians, and they're called the phase constants. Now, hold on. Let me just have the same kind of presentation as above. So these are phase constants, and they're going to be in radians. Okay, and they determine the initial conditions at t equals 0. That is the position and the velocity of the oscillator at t equals 0. Okay. Now, let's maybe go back to this real quick. Let's make a copy of this and bring it down here. This is rather important to understand. So we said you can use cosine or sine, and the truth is cosine and sine basically have the same graph. I don't mean that they're on top of each other. I just mean if you grab a cosine and you slide it over, it's going to superimpose with a sine curve at some point, and you won't be able to tell them apart. Right? So that's the same shape, they're just shifted with respect to each other. Okay. Now, the thing is that here at t equals 0, we're saying that x is equal to 0. But apparently, the oscillator is at equilibrium at t equals 0, and probably it's moving in the positive direction because I have a positive slope, and, well, dx dt, which would be the slope, is the velocity. So it would be moving to the right, maybe. Okay, that's one option. I can certainly have an oscillator that is moving to the right at t equals 0, and has a certain, is moving to right, it's equal 0. That's it. That's one option. But it doesn't have to be the case that that's true for all oscillators. Right? So I could have an oscillator, for example, maybe let me just do this. Okay, let's group these guys. There we go. All right. Maybe I have an oscillator that instead, at t equals 0, has x equals a. Okay, and then of course we would get rid of this part of the graph. But what you're effectively doing with phi is you're sliding this curve left and right so that whatever value you get at t equals 0 matches what your oscillator is doing at t equals 0. So is your oscillator going through the equilibrium position moving to the right, or is it at x equals a at one end of its oscillation and about to come back? That depends on the oscillator. It depends how you put it in motion. And so what phi sub s allows you to do is to say, okay, well, I know it's going to be a cosine or a sine. Phi is going to slide the cosine or the sine so that its initial condition matches the initial condition of your oscillator, and your curve describes the motion of the oscillator. Now we'll see how to do that in problems, but it's a really important thing to know how to do for oscillations, is to find omega, the amplitude, and the phase constant, phi sub c or phi sub s. Okay, so the goal was to explain this and hopefully understand why, in fact, it does indeed represent oscillatory motion. It is going to describe back and forth motion along x or along y, or maybe it's an angle theta that's oscillating, but this type of mathematical equation describes back and forth motion about an equilibrium position. Now, if indeed we have x of t that can be either cosine or sine, then let's talk about kinematics real quick, and then we're going to talk about the two main oscillators that we need to have in mind. Okay, so as a reminder, cosine of u prime is minus u prime sine of u, and sine of u prime is u prime cosine of u. Okay. So let's say we start with what effectively is going to be position. Now I'm using x of t, but again, it could be y of t, it could be theta of t, it could be angular position, right? But let's just assume that we start with a cosine here. And let's see what happens if instead we have a sine here. Okay, so I'm just going to cover both cases so that we've gone through all of them. All right, well, velocity is the derivative of position. It's dx dt, right? And cosine of u prime is minus u prime sine u. So I'm going to get minus a. U prime is going to be omega sine of omega t plus phi sub c. Careful. Effectively, this is u, right? So this is going to be phi sub c, even though now I get a sine, right? The sine came from differentiating, but what's inside of u is phi sub c, so I still get phi sub c in here. And let's maybe make a little bit of room so that we don't trespass too far to the right here. Okay, this is going to be x of t. What is it going to be here? Well, vx of t is going to be, if I take the derivative of sine, I'm going to get a omega cosine of omega t plus phi sub s. Again, this here is u. So u has phi sub s in it, and therefore it finds itself in here. Okay. So that's what velocity looks like. Now, by the way, if we said that this is basically amplitude, which means it's x max, right? It's the greatest value achieved by x. It is the furthest away from equilibrium that you will find yourself as you oscillate. Okay. Well then, with the same logic, this A omega is V max. So V max is A omega. That's the fastest the oscillator is going to go. That is a remarkably underrated equation of oscillations. It is extremely useful to know that V max is A omega. And then we're going to get acceleration. Right? A sub x of t is going to be dvx dt, and here we go again. We hit this with another round of differentiation. We're going to get minus a omega squared cosine. It's going to come back, omega t plus v sub c. Here we're going to get a sub x of t is going to be minus a omega squared sine of omega t plus v sub s. Okay. And with the same logic, because after all, this is the same math as this is the same math as this. This is the maximum acceleration that the oscillator will experience throughout its oscillation. It is the second most underrated equation of oscillations, which is A max is omega squared times the amplitude. Very useful to have V max and A max in mind when we solve problems. Okay. So that's for kinematics. Now, the goal here was twofold. First, it was to say, look, X max we kind of understand, right? It's if you oscillate, X max is how far you go from, with respect to your equilibrium position. So that's just your amplitude. And so now we can also define V max and A max. Now that's actually useful. The second reason why I went through these kinematic equations is to show you how ugly they are, which makes it quite unlikely that in fact we will solve anything with these equations. I'm not saying you can't. You can. It just involves trig identities and more math than we care to do typically. So whereas kinematics was a perfectly viable option at the beginning of the course if we wanted to find how fast the block is moving after 7 seconds or something like that, it is typically not what we are going to be doing when we deal with oscillations. Most of the time we're going to try to get our answer with conservation of energy. Now sometimes that's not possible, so it's not like it always works, but the first thing I should be thinking of is not kinematics. I should be thinking how ugly kinematic equations are and how far away I would like to stay from them if I can. And usually we can. There's minimal use of these types of equations. Most of the time what you're trying to do is find A, omega, and phi sub c or phi sub s. Okay, so oscillation is a very specific type of motion, back and forth motion with a period about an equilibrium position. It is governed by a very strange equation, which is a second order differential equation. Nobody cares that you know what it is or you know how to describe it. We only care that you know how to recognize it, and you can say that if x follows that equation, then it must be the case that x looks like this, one of these two. And looking like this means that you are going to oscillate with time back and forth. You will oscillate with an amplitude, a frequency, and a period, and a specific phase constant just to describe what's happening at the beginning of your oscillations. Okay, so now let's go over the two most classic oscillators that you need to have seen and know how to deal with so that we can recognize them in problems and feel comfortable dealing with them. Okay, now the simplest oscillator, and it's usually the one that we start with, is the mass spring oscillator. Okay, now that's very simple. It is going to be the mass attached to a spring, attached to a wall or something like that. And you are going to either pull the mass away and let it go or, launch it into motion. And it is going to oscillate back and forth between minus A and A. And if you do this on a frictionless table so that there's no energy loss, these oscillations will go on forever. And that's going to give you simple harmonic motion. Okay, those are the oscillations that we study. the back and forth goes on forever. And so at any given moment in time, the position of my oscillator is going to be x of t, some function of time that describes this back and forth motion. Now if I let this be y and this be x, and I write Newton's second law, then what do I get? Well, perhaps I'll write Newton's second law down here, because perhaps I want to draw a free body diagram of this thing. Okay, so it's going to be the normal force, the weight force, and then the spring force. Okay, and if this is the equilibrium position, that's the position where the spring is neither stretched nor compressed. However, if you're an amount x to the right of that, now your spring is stretched, an amount x, therefore it pulls back to the left with an amount kx, that's Hooke's law. Okay, so that's what we learned about before when we were talking about springs. Okay, well, Newton's second law says what? It says that F net x is equal to max. Okay, so minus kx is equal to max. So that means that m a sub x plus kx is equal to 0. And then I need to recall that acceleration is the second derivative of position, because v sub x is dx dt and a sub x is dvx dt, so okay, the second derivative of position is acceleration. Therefore, I'm going to find myself with, so long as I divide by m to put this in standard form, d squared x dt squared plus k divided by mx is equal to 0. To be compared to d2 squared dt squared omega squared x is equal to 0. Okay, so that looks exactly like the equation we stated at the beginning, meaning that x is going to oscillate because it satisfies this differential equation. Now, the beauty of this differential equation is that it actually tells me what omega squared is. It's this term right here. So what I get out of this is omega. And what I need to realize and keep in mind is that my omega is specific to my oscillator. Okay, so omega is always 2 pi f, which is 2 pi over t. This is always true for all oscillators, no question. But a given oscillator, such as the mass spring oscillator, will have a certain omega. And in this case, we're going to have omega is equal to square root of k over m. And that is oscillator specific. We'll see that when we do the simple pendulum in a second, we will find an omega, but it'll be a different omega. It's not going to be square root k over m. It's going to be square root of g over l. So that's omega. That means that the frequency at which this oscillator likes to oscillate is going to be omega over 2 pi, because omega is 2 pi f. So that's 1 over 2 pi square root of k over m. And then the period t is, well, it's 1 over the frequency, so that ends up being 1 over 2 pi square root k over m. Okay, which means that with this type of oscillator, I should say, if you set it in motion, right, if you pull it away, you stretch the spring and then you let it go, and it's going to go back and forth forever. It will do so at this very specific frequency. These are called free oscillations. The block is free to do whatever it wants. You just pull it away, let it go, and it starts going and it does its thing. And it will have a period that is equal to this, and therefore a frequency that is equal to this. There is nothing you can do about the frequency at which it oscillates because actually you decide to not do anything. You let it be free oscillations. Now, forced oscillations is something else. Forced oscillations would be like, no,
give me that spring, and you would grab the spring, and then you would shake the spring back and forth, and you would see what happens to the mass as you shake the spring back and forth. That would be forced oscillations. It's definitely a part of oscillations as a chapter if you want to cover the whole thing. That is not something that we do in this class. So we only do free oscillations. And what I'm trying to emphasize here is that there will be a certain frequency at which this block oscillates back and forth that is set by the spring constant and its mass. That's it. It is, by the way, independent of the amplitude. You can pull it further and let it go. It's going to have the same period. This just means that on average it's going to move faster. But that's an interesting property, is that the period and the frequency are independent of the amplitude. Okay, so that's the mass spring oscillator. Now, we could say more about it, but I'll keep that for the problems where we're going to introduce energy and we'll do conservation of energy. The other classic oscillator you have to know about is the simple pendulum. Okay. Now, the simple pendulum, that is going to be a massless string of length L with a point mass M attached at the end of it. Here's going to be our equilibrium position, right? Because if you leave it alone, it'll just hang vertically. So that is my equilibrium position. It would correspond to theta is equal to 0. And then what's going to oscillate here is not x, it's theta. That would be theta of t. And this thing is going to go back and forth like this and oscillate, in fact, forever, because we're going to neglect energy losses. In other words, we neglect air resistance, and so the pendulum never stops swinging. Okay? Now, let's make counterclockwise the positive direction. Let's call this our pivot. And in the same way that we applied Newton's second law to our mass and spring before, let's apply torque net equals I alpha to this thing, because after all, well, this is rotational motion by definition, right? It swings back and forth like this. Okay, so let's draw the free body diagram. We'll start with that. mg, strings can only pull, so there's tension toward the center here. And then I'm going to write Newton's second law, which is going to be torque net is equal to I alpha. Okay, that's going to be torque due to tension plus torque due to mg is equal to moment of inertia of a point mass, because the string has no mass. So moment of inertia of little m is ml squared with respect to my pivot times alpha. And the torque due to t is 0 because t has a line of force that goes through the pivot. Any force that has a line of force that goes through the pivot does not create any torque about that pivot. So we are going to find that the torque of mg, first of all, is negative. It tries to swing the rod clockwise, and clockwise is negative. The distance, L, mg, sine of the angle between L and mg, well, turns out that that would be this angle here, which is also theta. Okay, is equal to m L squared alpha. Now, interestingly enough, m goes away. It does not matter what the mass is. This L kills this L, and we are going to end up with L alpha plus g sine theta is equal to 0. Now remember that alpha is d2 theta dt squared, and so we're going to wind up with this. Now that's a little sad because we want to compare this to an equation like this, right, where we have d2x dt squared plus omega squared x is equal to 0. Okay, x could be anything. Maybe x here is theta instead of x. Doesn't matter, right? What we'd like to find is we want to find the equation
in this form, because then we know for sure the solution to that is oscillations, which is what we expect. Okay, well we can't because we are off just because of the sine theta, right? We want theta, we have sine theta, so that's a bummer. And so we fix that and we say, you know what? We will assume that the oscillations occur with a small angle. And the small angle approximation allows me to say that sine of theta is approximately theta. Okay, so long, of course, as theta remains very small in front of 1 radian. Okay, so if that can be said, then this indeed can be written like this. I'll divide by L on both sides. That's going to be d2 theta dt squared plus g over L, and sine theta becomes theta. This equals 0, and this is in the right form to yield oscillations, right? So we conclude that theta is going to oscillate. It will oscillate with an angular frequency, omega, that is the square root of g over L. And like I said earlier, omega will have a specific expression for each oscillator, right? Whatever comes out of applying Newton's second law, whether it's F net equals ma or torque net equals I alpha, if you can put that equation in the form, in the standard form, d2 theta dt squared plus omega squared theta equals 0, omega will be whatever it is depending on the type of oscillator that you have. Now it will always be related to f and 2 pi in the same way. Omega is 2 pi f, that's true, but omega itself is a function of the oscillator that you have. Okay, so f is equal to omega over 2 pi. That's going to be 1 over 2 pi square root g over L. And then t is going to be equal to 1 over f. And that's going to be 2 pi square root L over g. Okay. All right, so those are the two main oscillators that you're going to encounter. I'm not saying that there aren't any others. There are, but if you already know this about these oscillators, it's going to be easy to establish the differential equation for other oscillators and to find omega. So one thing I'll say at this point is that oscillations is one of those chapters where there's just a lot going on and it looks very different from everything we've done before. And so, well, you have to start somewhere, right? So we have to start by learning something so that we can start having conversations about oscillations and just get some practice. And so, did I cover everything? No. I covered enough so that we could somewhat have a mathematical foundation that is going to be common to all oscillators, and then somewhat see what type of oscillators we might encounter, what omega, f, and t is for each one, and by the way, how we found omega, either f net equals ma and torque net equals I alpha. And so that's kind of where I decided to start. We're going to learn a few more things when we do problems, and again, it's just one of those chapters where as you keep rehashing it, it makes more sense how everything is tied together. But if we give you everything in one fell swoop, it's not very digestible. That's a lot of information thrown out there all at once. All right, so let's do some problems. So I chose on purpose to do the following, which is to cover just enough so that we could understand what oscillations are and what oscillators might look like. And then I picked a couple of problems where I wanted to show you how you would study these oscillators, but also how you might find them showing up in problems. Right? Everything that we've learned before, for example, collisions or conservation of energy, is still going to be applicable. And this is a good example of of this, where we don't just have an oscillator all by itself. We have an oscillator, and then for which, we want to find the kinetic energy, and then the stored elastic potential energy, and then a bit of a technical question: at t equals 2 seconds, what direction is this oscillator traveling? Okay. So we have an oscillator with an equilibrium position here. It is going to oscillate back and forth between x sub m is 25 centimeters and minus x sub m. X sub m, or a, same thing. It's the amplitude. Okay. We know the mass, we know the period of oscillation. We're told that t is equal to 1.5 seconds, but we do not know, what do we not know? We do not know k. Okay, now we know, however, that k is going to be important because omega is square root of k over m for a mass spring oscillator, so omega is pretty important. It means it should be important to know k. But perhaps we can find k. Maybe we start with that. And then we can find the positions where the speed is 1 meter per second. Okay, and so that would be one of these positions, and we can relate that to, using conservation of energy, either this position here, or this position here. Now I will say something about this drawing because, the problems that I take from old exams or adjust a little bit, then I can maybe make changes to, but this one I haven't, and you 1, 2, 3. What am I trying to say? I'm trying to say I debated changing this figure, and I decided not to, on the condition that I would then mention a few things when it comes up. This is just, first of all, it's the same block, and it's meant to represent that it oscillates back and forth from here to here, back and back and back and back, right? Here we're just showing the equilibrium position. Here we're showing some position where v is 1 meter per second. Okay. Now, worth noting that it is at the endpoints that velocity is 0, because that is where the oscillator turns around. Okay, turnaround points are points where velocity is 0, right? It's no longer moving out, but it's not yet moving back in. Momentarily, v is 0 at the endpoints. What is certainly not the case is that v is 0 at x equals 0, even though maybe it kind of looks like it. Okay, but let's assume that we're moving to the left. Now, half the time when m goes through the equilibrium, it goes to the left, but then eventually it comes back and it's go through the equilibrium to the right. But let's assume that this came first and then a little later it's here. Well, here v is not 0. In fact, here v is v max. All right, so an oscillator will reach its max speed when it goes through its equilibrium position. Okay, because it's been speeding up from 0 here, being pushed to the left by the spring, reaches here with v max, and then the second it steps over the line here, x equals 0, then the spring is going to start to be stretched. It's going to pull it back, and it's going to slow it down to a stop, and then it's going to come back. So as the mass goes through the equilibrium position, it reaches its max speed. And by the way, the acceleration here will be 0, because at the equilibrium position, this spring will neither be stretched nor compressed, because we have horizontal oscillator. And then here, we're going to have max acceleration. Here, we're going to have max acceleration as well. So max velocity or max speed occurs at the equilibrium position. Max acceleration occurs at the endpoints. And then conversely, v is 0 at the endpoints. Acceleration is 0 at the equilibrium. So that is, I did not want to change the figure to reflect that. I figured it's more interesting to talk through it, but it is worth making note of that, even though it's not directly relevant to what we're trying to do right now. Okay, so right now, we are going to first try to find k, but that's doable because we know t, the period of oscillation, and then we're going to find the positions where v is equal to 1. Okay, so I know that I have a horizontal mass spring oscillator, and therefore omega is square root of k over m. Now omega, by definition, is 2 pi over t. So 2 pi over t is square root of k over m, meaning that 4 pi squared over t squared is equal to k over m. Thus, finally, k is equal to 4 pi squared m divided by t squared, which is going to be 4 pi squared multiplied by a mass of 1 divided by 1.5 squared, and that is going to be approximately 17.54 Newton per meter. Okay. Now, if you're wondering, well, why did you find k even though nobody asked you to? Fair enough, it's not obvious right off the bat. But what we're about to do will convince you that we actually need k. So if you wanted to start with conservation of energy, which is what I'm going to do, then you would very quickly realize that you need k, and so you would, sidebar that and go find k by doing whatever I just did, and then you could return to conservation of energy. Okay, so let me write conservation of energy. Now, by the way, how do I know that I have conservation of energy? Well, I have conservation of energy because the surface is frictionless. It must be, because I want my oscillations to go on forever. And so there's no friction. The normal force doesn't do any work. It's perpendicular to displacement. The weight force doesn't do any work. It's perpendicular to displacement. The only force that does work is the spring force that drives the entire motion. The spring force is a conservative force. Therefore, if the only force that does work is a conservative force, I get to apply conservation of mechanical energy. Now, what points do I choose to apply conservation of energy if I want to find the locations where v is equal to 1? Well, I should pick this point for sure because I want to solve for that x, and then I can relate it to, I don't know, any other point. It doesn't really matter, right? So maybe we choose this point here where v is equal to 0 because I know what xm is, so that's helpful. So I will write that 1/2 kinetic energy, 1/2 mv squared, plus potential energy, 1/2 kxm squared, that's going to be here, is equal to 1/2 mv squared plus 1/2 kx squared. Now this is not a great notation, maybe I'll call it Vm. It's not Vmax though, it's just Vm. The point is that it's 0 at x equals xm. Okay, x equals xm is a turnaround point. You made it, that's the amplitude, 25 centimeters. So you're momentarily stopped at that location. Okay, and so what am I solving for? Well, I'm solving for this guy, given that I know that this is 1 meter per second, v, right? So all the halves can go away. I'm going to get kxm squared is equal to m v squared plus kx squared. That means that kx squared is going to be kxm squared minus m v squared. I will divide both sides by k and then keep the positive root. Now, I say that, but maybe I went a little fast there. Do I keep the positive root or do I keep the negative one? Or in fact, do I keep both? So, here's an important note. We've done this so many times at this point. And if you go back to the very first live stream I did,
I warned about this, that this is an issue in physics when we're doing kinematics, that we go from a squared quantity to the square root so many times where what we're looking for is positive, that we're like, yeah, I know it's plus or minus, but I just want the positive root, so forget it. I don't need the negative root. And it becomes such a habit that it's very easy here to forget that you need both, right? The motion is symmetric. If this location here is going to be where v is 1 meter per second, then there's going to be the same location right here where v is going to hit 1 meter per second as well. Okay, so we need to consider two roots, plus or minus. The square root of xm is 25 centimeters, so that's 0.25 squared, minus m, which is 1, v, that is 1 squared, divided by k, which is 17.54, whatever that is. And this is going to be plus or minus 7.4 centimeters. Okay, so when x hits 7.4 centimeters to the left or to the right of equilibrium, of x equals 0, it will be moving with a speed of 1 meter per second. Now, to the left or to the right, we don't know, right? Because, yeah, okay, right now this thing is coming in like that, but at some point it was being pushed away and it went through this point and it had 1 meter per second the other way. But at least we know that these are the locations where v hits 1 meter per second. Okay, so the next question is, what is the kinetic energy of the mass at those positions? What is the stored elastic potential energy U spring at those positions? Okay, so we have this thing here. Let's bring it down here. And we know that at x equals plus or minus 7.4 centimeters, the speed v is equal to 1 meter per second. So the kinetic energy at those locations is going to be 1/2 mv squared. That's very easy. So that's 1/2 times 1 times 1 squared, which is 0.5 joules. That's by definition, right? It's just 1/2 mv squared. What is the elastic potential energy U spring? Well, that's going to be 1/2 kx squared. And we know what x is, right? So this is going to be 1/2 times 17.54, that's k, times x, which is, okay, so it's 7.4, but it's 7 centimeters, so 7.4 10 to negative 2 squared, and that's going to be approximately 0.048 joules. All right, so that's K and U spring. Okay. And then finally, at t equals 2 seconds, in what direction is the block traveling? This is a great question. Okay, so this is super fair game. Okay. And let's go back real quick. Sorry for all the scrolling. I'm going to erase this. Allow me. I'm just going to clean this up because we don't need any of this anymore. I just want this. Okay. Now I am told that at t equals 0, this thing is released from rest here. That's my initial condition. All right, so my initial conditions are the following. At t is equal to 0, x is equal to xm, which is 25 centimeters, and v sub x is equal to 0 because the block is initially at rest. Now in general, I need both. In some cases, I only need to know the initial condition on x.
And that's typically what happens here.
But in general, you need both, and there's a whole bunch of problems where you use the fact that you need both to figure out what the phase constant is, which we'll get to. But here we're going to start with a simple example just to get warmed up. Okay, so I need to figure out at t equals 2 seconds, are we moving to the left or are we moving to the right? And then to do that, I have to figure out, well, what's going to tell me that? Now, what's going to tell me that is velocity. Velocity will be positive if I'm moving to the right. Velocity will be negative if I'm moving to the left. And I said before, as long as I can avoid kinematics, I will. However, if you ask me a question about time, typically that is by definition a kinematics question, so there's no getting away from it. I'm going to have to figure out Vx of t, which means beforehand I'm going to have to figure out x of t.
Now, x of t is going to be of the form a, cosine or sine, I'm going to pick cosine, omega t plus phi sub c.
Okay.
Now, what is a? A, by definition, is xm and is 25 centimeters. So I know the amplitude. Now, it's usually easy to find the amplitude. A lot of the times it's just given. Omega, okay, well, omega is square root k over m, and I could compute that if I want. I could also say that it's 2 pi over t, okay? But omega is equal to this. So I know A and I know omega. Now I don't really need them, so I'm not going to make a big deal out of it, but if I wanted to find everything, A, omega, and phi sub c, well, I'd start probably with amplitude and then work my way through them. And if I needed them, I could use them. I could say A is 25 and omega is root k over m. I can compute that, whatever that number is. Now I don't really need that to find phi sub c. Okay, so to find phi sub c, let me do this. This would be doing it in order, right? Okay, and so then to find phi sub c, we'd have to use the initial condition, right? The initial condition is that when t is equal to 0, x is equal to xm. So x at t is equal to 0 is equal to xm. That means that a, cosine of omega t plus phi sub c, when t is 0, so in other words, when omega t goes away, is equal to x sub m. Well, yeah, okay, no, that's right, x sub m. Okay, but since a is x sub m, I get x sub m cosine of phi is equal to x sub m, which of course simplifies, and cosine phi is then equal to 1, not 0, please. Okay, you divide both sides by xm, you don't get 0 on the right-hand side, you get 1. And, well, that's easy because there's only one angle that has a cosine of 1, and that's 0. So phi sub c is going to be equal to 0. Okay, so if I choose cosine, I get phi sub c is equal to 0. If you go ahead and you try it with sine instead, you're going to find that phi sub s is going to be pi over 2. That's okay, you just carry on. That's what you put back in here. Right? That's the value that you have. Okay, so I know everything. Let me, you know what? Let me just do this so that we have it. It's the right thing to do. Omega is going to be equal to 4.19. radians per second. Okay, so I know everything about x that I would want to know. Why did I want to know x? Well, not because I really care about x, but because I need x of t. In other words, I need to know that x of t is equal to xm cosine of omega t plus 0, so just cosine of omega t, so that I can then say that v sub x of t is equal to the derivative is going to be minus xm omega sine of omega t. And the reason I want velocity is that I want to plug in t is equal to 2. If it comes out negative, we're moving to the left. If it comes out positive, we're moving to the right. Okay. And so, okay, then at t is equal to 2 seconds, Vx of t equals 2 is equal to minus 0.25, that's 25 centimeters in meters. Omega is 4.19 sine of 2 times 4.19. That is going to be approximately minus 0.15 meters per second. And because that's negative, we conclude that the oscillator is moving to the left at t equals 2 seconds. So the oscillator moves left at t is equal to 2 seconds. All right. Okay, so that's an example of the types of questions you might get. It's a decent problem. It's not the hardest problem that was ever written when it comes to oscillations, but it's a decent one to kind of, use everything we talked about before and see how you might find, for example, the amplitude, omega, and phi to find x of t and then vx of t, so on and so forth. Okay, let's, excuse me, let's look at this problem now. And I did one of each, right? The mass spring oscillator and then the simple pendulum oscillator. Okay, so I have a simple pendulum with a length of 20 centimeters and mass of 1 kilogram, pulled 5 degrees away from its equilibrium position. At what angular speeds is the speed of the mass equal to 0.1 meter per second? Okay, well, that is a similar question to what we just solved for the horizontal mass spring oscillator, right? So I'm going to exaggerate the angles just so I can see what's going on. Okay, this is obviously much bigger than 5 degrees, but I'm just saying theta m, which is my amplitude, theta m is going to be 5 degrees. That's what we're given that. And V initial is going to be 0 because I release this thing from rest 5 degrees away from the vertical. Okay. And I want to find the positions where V is 0.1 meter per second. Okay, so let me draw this again at a different location. Maybe a little lower down like this. And I would like here to have V equal to 0.1 meter per second. And this is going to be some angle theta, and I'm solving for theta, and that's what I want to find. Now I'm going to use conservation of energy, just like I did before. How do I know? Well, I have the weight force that's driving the motion, and then I have tension force. Tension force is going to be, at all times, perpendicular to the displacement, so it will not do any work as we swing down. Therefore, conservation of energy applies because the only force doing non-zero work is the weight force, which is a conservative force. Okay, so I'm going to use conservation of energy, and to do that, I need to track not just the kinetic energy, which can be pretty easy, but the gravitational potential energy of this thing. Now I'm going to take potential energy is going to be 0 down here at the bottom of the swing. Okay, so when the mass makes it down here, it has 0 potential energy, and right now it has a certain amount that is based on this height that I'm going to call h initial, And here it has a certain amount based on this height that I'm going to call h. Now it is fundamentally important that you know how to find h initial and h. Of course, you find both the same way, but my point is, if you do not know how to do this, you're in big trouble. Like, there's no, I would probably stay in bed the day of the exam, because this is such a classic question that you really need to know how to find h. Okay, now let's see. I have a length L here. And if I say that this is my reference, which is not to scale, when the pendulum swings down and it's at its lowest point, well then it turns out that all of this, is also L. That's the key. Okay. Now, h initial is going to be all of L minus this piece. The question then is, what is that piece? Okay, well, that piece is easy to find. It is going to be L cosine theta m. The same logic applies here. All of this is L, yes. This length here is going to be L cosine of theta, which means that h initial is L minus L cosine theta m, which we typically write L1 minus cosine theta m. And with the same logic, h here is simply going to be L1 minus cosine theta. Okay. Well, let's write conservation of energy. Conservation of energy is going to look like what? Well, kinetic energy at the beginning is 1/2 mv initial squared. That's going to be 0 because we start at rest up here, plus gravitational potential energy. That's easy. That's mghi, so that's mgl 1 minus cosine theta m. That's going to be equal to, let me preemptively make some room, it's going to be equal to, now on the right we have kinetic energy 1/2 mv squared, and we know what v is, plus mgl 1 minus cosine theta. All right, let's go. M is going to drop out. Okay, and I want to get my hands on theta. So let's see what we can do. Let's first multiply everything by 2 to get rid of the fraction. We're going to get 2gl minus 2gl cosine theta m is equal to v squared plus 2gl minus 2gl cosine of theta. Okay, this is going to cancel with this, and I'm going to get, okay, that was, I've had brighter moments. Should have divided everything by gl. It's okay. 2gl cosine theta is v squared minus 2gl cosine theta m. And so cosine theta is going to be v squared divided by 2gl minus cosine theta m. And by minus I mean plus. It turns out, because this came to this side, so it became plus. Okay, that makes more sense. Okay, So then theta is going to be equal to, well, plus or minus, because cosine theta and cosine minus theta are the same thing, inverse cosine of this and that's going to be plus or minus the inverse cosine of v squared, which is 0.1 squared, divided by 2 times 9.8 times 0.2 plus cosine of 5. And that's going to be approximately 2.87 degrees, plus or minus. Okay, makes sense. It's smaller than 5, yeah. If it had come out bigger than 5, that would not have made sense, but okay, smaller than 5, I buy that. I swing down from 5. At some point, my speed hits 0.1 meter per second. Okay. All right, the next question asks, what is the kinetic energy of the mass at those positions? Well, that's easy, right? At theta is equal to plus or minus 2.81 degrees, K is equal to, well, it's just m1/2 mv squared. In fact, I mean, I already know what v is, so I don't need to solve anything other than to just write, 1/2 times the mass, which is 1 times the speed of 0.1 squared. Well, that's going to be 0.005 joules. Okay. And then at t equals 2 seconds, what direction is the pendulum swinging in? Okay, so same question as before, right? So we're going to do the same thing. So we start at t equals 0, we start at an angle theta m is 5 degrees, v is equal to 0. This is at t equals 0. Okay. Now, if I need to find whether it's swinging clockwise or counterclockwise, I first need to decide what I'm going to call positive. Now, typically, counterclockwise is positive. And I need to find omega, really, as a function of time, which means that I have to know theta first. Then I'll find omega by taking the derivative. I'll plug in 2 seconds and we'll see what we get. Okay. So theta of t, because now what oscillates is theta, it's not x. Theta of t is going to be of the form theta m. Well, okay, no, let me do this. I'll call it a. And now I used cosine before. Let's use sine this time. Sine of omega t plus phi sub s. Okay. Now a is the amplitude. That's theta m. That's 5 degrees. Okay, now the problem is we shouldn't leave it in degrees. We need that to be in radians, okay? And so 5 degrees in radians is going to be not very much. So this is 0.0872 radians, okay? But that would be my amplitude, right? Okay, what about omega? Well, omega is going to be square root of g divided by L. Let's compute that so that we have it too. That's going to be square root of 9.8 divided by 0.2. Let me quickly do that. Square root of 9.8 over 0.2. That's 7, actually. Oh, that's interesting. Okay, sure. 7 radians per second. Okay, so I know the amplitude. It's theta m, really. I know omega, and I use the formula that is specific to the simple pendulum, right? Square root of g over L. And then I need to find phi sub s. Well, to find phi sub s, I need my initial conditions, right? So at t is equal to 0, theta is equal to theta m, and then omega, now careful, this is where it gets tricky. Let me write it like this. Okay, this is actually good that we bring this up. So I'll write theta at t is equal to 0 is theta m. We agree. Okay, we pulled it away 5 degrees. At t equals 0, we let it go. Omega of t is equal to 0 is equal to 0. That's the angular velocity. Not to be confused, unfortunately, with omega, which is angular frequency. Now, there's a good reason why these two letters are the same, but it does make it crazy confusing. So one thing that you might want to do, which you might find in some books, is that we call this omega naught instead. To say, well, it's a special omega proper to the simple pendulum, it's square root g over L. And for the mass spring, it'd be square root k over m. So you could do that if you don't want to get confused, but I'll just stick to my notation, but be very careful, don't confuse angular frequency and angular velocity if you have a pendulum. Okay. So, if theta at t equals 0 is theta m, it means that I have the following. It means that this thing here, when t is equal to 0, is equal to theta m. So in other words, it means that theta m sine of omega t, which is 0 because t is equal to 0, plus phi sub s is equal to theta m. That means sine of phi sub s is equal to 1. The only angle that has a sine equal to 1 is pi over 2 radians. All right. So in other words, if I have theta m is 0.0872 radians, omega is 7 radians per second, and phi sub s is pi over 2 radians, then this expression here will properly describe my angular position over time as this pendulum swings back and forth. Okay. Well, if that's the case, then I'll take theta, which is theta m sine of omega t plus pi over 2, and I will compute omega t, right? This is the angular velocity again, it's d theta dt, because if I do that, then I can plug in t equals 2 and see if it's positive or negative. And if it's positive, then we're going counterclockwise. If it's negative, we're going clockwise. Okay, so I get omega theta m cosine omega t plus pi over 2. And at t is equal to 2 seconds, theta t is equal to 2 is going to be omega, which is 0.0872, is that true? Yes. Times theta m, well actually that is theta m, so my bad. Omega is 7, so this is 7 times this, cosine of 7, that's omega, times t is 2, plus pi over 2. That is going to give us minus 0.605 radians per second. And so, and yikes.net, sorry, Jesus. This is not theta. Obviously it's omega. Angular velocity tells me which way I'm going. Negative clockwise, positive counterclockwise. Okay, so since omega at t is equal to 2 is negative, we conclude that the pendulum is swinging clockwise at t is equal to 2 seconds. Okay. All right. So hopefully that gives an overview of oscillations that's a bit more compact than like going through the whole thing in one fell swoop. I tried to touch on enough things that if you go and solve other oscillations problems, you would probably encounter at least some of this in some form. And hopefully talking about the math like we did at first, which is not always emphasized, at least helps understand where all of this comes from. Again, you're not supposed to be an expert at differential equations like these. Nobody expects you to know that the solution to this equation is oscillations and that it looks like this. I mean, yeah, now we expect you to know because we said it, but we never expected you to unearth this equation, look at it, and be like, oh yeah, right, I remember how to solve these. This is the solution, right? Nobody's asking you to do that. But we do want you to recognize that if you have an equation of that form, the quantity x, whatever it is, if it's x or y or theta, will oscillate, and it's going to be oscillating according to a function that looks like this or like this. And then you have to understand what amplitude is, what omega is, what the phase constant is, and you have to be comfortable finding these quantities if you're provided enough information. And then, of course, you know, we dive into specific oscillators, and I only did the two most common ones, the mass spring oscillator and the simple pendulum. But if you understand those and you can derive omega for those, or even use conservation of energy like we did, that's a good baseline for the other ones. You'll find that the other ones solve the same way. Maybe it's a little bit more technical for, you know, some torsional pendulum. That's what I was looking for that name, or the physical pendulum, which would not be like the simple pendulum is just a string that has no mass, but you don't have to have a string, right? You could just take a rod and then it would have a mass, it would have a moment of inertia, torque net equals I alpha and all of that. Maybe that's a little bit more complicated, but it's not that bad. And you'll still make the small angle approximation. So hopefully that kind of clears everything up. But as I said before, oscillations is just really one of those problems where, those chapters where you have to take it from some direction, you have to attack it from some angle and start doing stuff. And then as you do examples and problems, you're gonna, you know, do a little bit of that, be, oh, okay, maybe a little bit of this, oh, conservation of energy or whatever. And eventually it kind of all comes together once you practice enough. But it's not obvious right off the bat how all these oscillators are related and how similar they are. So that was my goal. Anyway, hopefully that made sense. As always, thank you for watching.